Hello everyone, good to see you again. And what are we going to do today? I don't know, I'm about to find out. If you're new to this live stream, welcome. What we do here is we talk about math that is inspired by questions that are asked by anybody. And the kind of math that we talk about is generally math that's around the algebra or geometry level, although that's the kind of math we use to explain what we're talking about. In fact, the kinds of questions we're talking about generally aren't questions that are from algebra or geometry themselves. Rather, they are questions that range across all of mathematics, science, and applications. And so, I welcome you, if you're new here, to ask whatever you're interested in, or to see what everyone's discussing, because then we'll be able to have an interesting conversation. If you have been here before, welcome back. It's wonderful to have this opportunity to talk to you every day as we think about math and the world. What should we discuss today? Let me see what I have here. So somebody said it's muted for them, but I think it'll be okay. It seems like the rest of the people can hear. And I see also that people have noticed that the blue shirt is back. Actually, the reason the blue shirt is back is because, and this is also part of the reason why this was slightly delayed. I was actually just interviewed for a media publication, and so we were doing the interview with this equipment, because nowadays you can't just go to the media station to go and talk to the reporter. About games, please. Someone wants to talk about games. Right, so games are pretty interesting. You know, let's see, what kind of game can we play? I have an idea. Okay. So when we think about games, a lot of times these games are games with two different players. Now, there's a particularly interesting game out there, which some of you may have heard before, and maybe we can play this together. And this is a classic, and please don't use this on your friends at school. So the game is very simple. It's just that we take turns. We take turns, and we choose a number. So as we choose this number, you know, there are these numbers we can choose between. There's numbers 1, 2, 3, 4, 5, 6, 7, 8, and 9. And we're just going to take turns choosing numbers. But now, how do you decide who wins? Well, you win as soon as you choose 3 numbers that add up to 15. Does that make sense? So here's a game. We'll take turns choosing numbers. And as you take turns choosing these numbers, we go and see who's the first to get a sum of the 3 numbers being 15. Oh, by the way, I mean sum of 3 of the numbers being 15. Take turns choosing numbers. The first person to get... You don't need to have only 3 numbers. If I had picked like 5 numbers, then if 3 of the numbers add up to 15, then you win. First person to get 3 of their numbers adding to 15 wins. That is a strange underline. Wins. Okay? So does the question make sense? The game is somehow, you know, you choose some numbers. We'll take turns choosing numbers. There's one player and there's another player. And as these 2 players are choosing numbers, they'll have a bunch of numbers. And at some point, if it turns out that 3 of the numbers add up to 15 of the numbers they have, then they win the game. It could be a tie. If it ends up being that they pick and somehow, unfortunately, neither of them has it, then it's, you know, doesn't work. And also, you can't pick a number that the other person already picked. Does everyone understand the game? The game simply just says that, you know, you take turns choosing these numbers, and let's see who can make the first choices that add up to 15. So let's play the game. How can we play this game? I guess we should go and have some people take turns, right? So, what's a good way of deciding how to do this? I don't want to play against you because I already know how to play. So let's just see. I'm just going to, let's do this. This is going to be very funny. We're just going to choose numbers based on what I'm seeing in the chat. So I see that the player 1, I don't know who's player 1, but player 1 wants to choose 5. Okay? So player 1 is green. Player 1 chose 5. Okay? Now what's player 2 going to pick? I'm just going to look and see what kind of numbers I see on this chat. Player 2 is going to be blue, I guess. I see a lot of 3s, so I'm just going to say maybe player 2 chooses 3. All right? We're sort of playing randomly right now. What should player 1 choose next? So what should player 1 choose next? I'm just looking at this list to see. I see somebody wants to pick 4913, but unfortunately that's not here. I'm just looking to see if there's a bunch of numbers that repeat. Okay, I saw a bunch of 7s. People like 7s. So player 1 chooses 7. Why in the world would you choose that? Okay, player 1 chose 7. Now what's going to happen next? What's player 2 going to choose? So I see there were a lot of 7s. I see that there's some 9s. Looks like people want to have player 2 choose 9. Player 2, I guess, can choose 9. Anyone win yet? Not clear. Oh yeah, by the way, how do you win? You need to get 3 numbers that add to 15. Gee, that's really annoying, because 5 and 7 add up to 12, and I need the 3, but the 3 is taken. I see a lot of 2s. Okay, somebody says that player 1 should choose 2 next. Okay. Right, we're trying to add up to 15, right? And unfortunately, we don't have that yet. So what should we do next? I guess it's now player 2's turn, blue's turn. What do you want? Player 2 can take 4. I saw someone saying player 2 can take 4. If player 2 takes 4, unfortunately 3 plus 4 is 7, 7 plus 9 is 16, it didn't work. Can player 1 win? 7 plus 5 doesn't work. 7 plus 2 is 9. 9 plus... Oh, wow! Wait, can player 1 win? Player 1 just needs to get a sum of 15. Does anyone see a way that player 1 can get numbers so that 3 of the numbers add up to 15? I think you can. I think player 1 wins if player 1 just picks... What number? Maybe I can't add. Is there a way to make them add up to 15? I think so. Because 7 plus 2 is 9. I see everyone's answering now. 6! Boom! And player 1 wins. Because 6 plus 7 is 13. 13 plus 2 is 15. Oof! It looks like player 1 has won. Okay, so that's the game. That's the game. Does anyone know a good way to play this game? I hope the game makes sense to you. The game here is just called I got 9 numbers, and I'm just going to go and try to pick numbers and take turns and decide who can get, get their numbers to add up to 15 first. Get 3 of their numbers to add up to 15 first. Okay. Block your opponent. Right, so we're starting to think about game theory. Okay, so let's do this. I think we need to go and find a way to keep playing this game because we need to be able to understand how to play this game. I have an idea. So all of these different people on this chat have different usernames. And so what I'm going to say is the game is now going to be if your username starts with A up to M, is M's the 13th letter, right? If your username starts with A through M, you're on player 1's team. And if your username starts with N and higher, you're on player 2's team. If your username starts with a number, or if it doesn't start with a letter, then let's just put you on player 2's team, okay? So that's how we're going to play this. We're going to do this once again. And this time there are 2 teams based on your username. A through M beginning is the first player, and N through Z and anything non-alphabetical is the second player. Here are the numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9. And what I'm going to do is I'm going to look at what people are suggesting to do. So player 1's going to go first. And I see, let's see, what do you want to do? I'm just going to look and see if I see some numbers streaming in. What would you choose for player 1? Does someone have an idea of what's a good first move? Player 1. Let's strategize. I see 5s. I see a lot of 5s. 5 is a pretty good idea. Oh, I like green. 5 is a pretty good idea because 5 is kind of a third of 15. Okay, it's player 2's turn. Player 2, what do you want? Player 2, I'm just going to look in the chat, and I see that there's a bunch of people who want 9. I see Paperboy was one of the first people, and a bunch of others want 9, going all the way out here. Okay, player 1, what do you want now? Let's look at this chat. Player 1. And we're going to look at the people who have the alphabetical from A through M. What do we see? We're almost doing some kind of a voting. I see a lot of 6s. I saw a whole stream of 6s. So player 1 chose 6. Somebody has asked, what is the question? And you can't tell what's going on because we're just voting with numbers, right? If you just came here, we're taking turns, and we're trying to see which team can get 3 of their numbers to add up to 15 first. All right, it's player 2's turn. And player 2, I see a lot of 4s, 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 4s. Everyone wants 4s. Oh, I understand why you want 4. Oh, good. You guys are trying to make sure you don't lose. Because, look, if player 1 took 4, game over. So player 2 chooses 4. All right, player 2, you've just blocked player 1. This is pretty good. All right, player 1's turn. You guys are smart. Thank you, V4913. Player 1, what do you want? Oh, I see that player 1 is also smart. Player 1 is saying 2. Lots of people are saying 2. Why do you want 2? It's because you're afraid of the 9 and the 4. 9 plus 4 is 13, and 13 plus 2 more is 15. Okay, good. It's player 2's turn. Gee, this is actually kind of fun. I didn't realize that we could in fact do this. So player 2, what do you want? People are thinking. People are trying to see if there's something I need to block. Okay. I see a lot of people are saying 8. Some people are also saying we lost. Really? So I see a bunch of people saying 8. And a bunch of people are also saying they lost. Why? Okay, first of all, why do they want to take 8? Because 8 plus 7 is 15. Why do you care? I'm not entirely... Maybe I'm... Oh, there's 7. 2 plus 5 is 7. So they wanted to block it with the 8. Right? 2 plus 5 is 7. 7 plus 8 would be 15. Okay, player 2 went to 8. How about player 1? Uh-oh. What does player 1 want? What else can you do? Player 1 went for 7. Because 7 plus 8 is 15. And you can make 15 with this. Okay, so that was the game. No, well, you know what? Let me tell you, this game, some people do not like this game. Let's go player 1. Does this game remind you of any game you've ever played before, by the way? There's no hope for playing second. Are you sure, Philip Neller? Well, this is a very interesting game. Does this game make you think of any game you've ever played before? Does this game remind you? Does it feel like any game? Oh, Winter Rain says tic-tac-toe. This is tic-tac-toe? Are you sure? This doesn't look like tic-tac-toe to me at all. But there's some similarity. It's like 3 numbers, right? Let me tell you where I got this game from. There's a really interesting museum in the world. It's called the National Museum of Mathematics. It's in New York City, Manhattan. And in this museum, there's a very, very interesting display. The display looks like this. You have a big board, right? There's a big board, and there's the instructions on the board. And the instructions on the board say, we're going to play this game, and this game has some levers, and the levers are like this. It's like, there's like a slot. Oh, maybe I can try to draw it like this. I'm not sure that would make any sense. But it's basically, imagine I'm playing against you, and there's this board in between us. The board has the instructions of how to play the game, and we're just looking at the instructions. And underneath the board, there are some levers. The levers start with all 9 of the numbers in the middle. And what you do is you take turns grabbing a lever, and pulling it to your side. So you either pull it to your side, or you pull it to the other side. Yes, I saw somebody say square-wheeled bike, or trike. There's a square-wheeled tricycle in this museum also. This is a very, very interesting museum, okay? So the setup is instructions on a board, and then underneath the board, some levers, 9 numbers, and each of the numbers has like a number on it, 1, 2, 3, up to 9, and you can grab the lever and pull it to your side. So on my turn, I pull 1. And on the other person's turn, they pull 1 the other way, right? And you take turns pulling. But here's the interesting thing. When you go towards the exhibit, the instructions on the board are exactly what I just told you. When the other person playing the game goes to their side of the board and looks, the instructions are very different. The instructions on the other side of the board say this. You know, the side of the board that you're looking at, that when you walk into the museum, just says, find 3 numbers, be the first to get 3 numbers that add to 15. On the other side of the board, there's a picture that looks like this. I'm trying to remember how this works. 2, okay, 7, 3, and I guess 9. And the other side of the board just says, play tic-tac-toe. That's all. The other side of the board says, just play tic-tac-toe. Oh, it's a magic square. Look what just happened. This is 15. This is the same game. This is actually, legitimately, the same game. If you look at what player 2 gets, player 2 gets this nice magic square. And player 2 says, I just need to get 3 on my side. Because, look, 6 plus 1 plus 8 is 15. 7 plus 5 plus 3 is 15. 2 plus 9 plus 4 is 15. All of the rows and all of the columns add up to 15. And also each of the diagonals adds up to 15. And the important thing is it turns out that there's no other 3 numbers anywhere here in the magic square that add up to 15. The only place that you can make a sum of 15 is the place that wins in tic-tac-toe. This is insanely cool. Yes, this is cool. I actually want to say, when I went to this museum of mathematics, I thought that the square-wheeled tricycle was cool. But then when I got to the basement and I saw this thing, I said, this just is an amazing museum. Because this shows you the value of math. If you don't know how to show that 2 things are exactly the same problem, you sometimes end up solving a problem all over again. But with math, you can just go and say, oh, by the way, it's the same as something I've already solved before. So now you can see what actually happened, right? In this game, what happened is first, I think the first player chose 5. Then the second player chose 9. Oh no! Do you remember from the earlier live stream? We did something else earlier in this live stream where we talked about how to not lose tic-tac-toe. And unfortunately, in tic-tac-toe, if you choose one of these squares on the side, you lose the game. So that's actually what happened. What happened is that, unfortunately, player 2 chose a square on the side. Then it's over. Yes, Shireen Zhang, you're right. Oh, we got to pick a corner. And actually what this also shows is that it'll be a tie game. Now that everyone knows how to play this game, it'll be a tie game. And indeed, if you look at how this game went, what was next? It was like 5 and then 9. I think the next one that was chosen... Wait, yeah. The next one that was chosen after 5, was it 6? Yeah, the next one chosen after 5 was 6, I think. So then, player 1 chose 6. And after the 6, player 2 said, oh, stop them, pick the 4. Right? It's just like tic-tac-toe. And they blocked it with a 4. And then player 1 said, whoa. There's a 4 and a 9. I better stop it with a 2. And then it was over because there were 2 ways for player 1 to win. That's exactly what happened. So this just shows, this is a fun game. It shows that game theory can be used to go and analyze things that look like they have nothing to do with a game you've played before. Great. So that's maybe that's what I thought of telling you about this game theory. And I will say I never expected that it would work so well to just go and play this with our YouTube live stream audience. Great. Please do not use this to trick your friends at school. That would not be a good thing. Okay. What else can we do? More questions. What are we talking about? We were talking about a game, but let's move on to another topic. We're about to choose something else. Temp ID says, you just use this as test dummies. No, you aren't dummies at all. You were figuring out how to do this, and you did quite a good job. I wouldn't say I don't think I was using you as test dummies because I have nothing else that I'm going to use this for afterwards. Actually, when I was thinking of doing this game, I was like, I know how I can do this game in a normal classroom, but I was not exactly sure how we could do it on YouTube Live. But we solved that together. What else do we have? Okay. So Michael Dong wants me to pick a question. He's been here since the beginning of the live stream. Does coding help with math? Yes, I think so. I think that people who write programs are used to thinking already in some fairly logical ways. And one thing that you do a lot when you're coding is you're writing functions. You write these functions that take some things going in and they spit out some other things. And that's like one of the most important concepts from mathematics that takes people some time to appreciate. So I think that coding does help a lot. And I've also noticed that people who can code quite well are just really good at putting together complicated things. And in fact, in math, some of the parts of math that are hard are when you're trying to put together a lot of complicated concepts. So coding helps with math, and by the way, math helps a lot with coding also. What else do we have here? Somebody said deep learning is the most. Well, yes, deep learning is something that you use a lot of math to do to try to find patterns in the world. And someone said, for some reason, TemptID said, for some reason, I learned functions in programming first. I think I might have also had that kind of an experience, because when you're writing programs, it's very natural to make a function. And then when you look at it in math, you're like, yeah, it's the same concept. I see that someone wants me to talk about a nautilus shell and the area. So I'm not entirely sure I understand what that person is saying, but I can try to do, I think I can try to do something with circles and a nautilus shell. Let's just try. Maybe that's what they want. Or maybe what I'll do is I'll talk about perimeter, because that's an easier thing that I can see immediately to turn into an interesting problem. And this is something which maybe you've seen inside this live stream before, where we drew a picture like this. So we started by taking a square, and then we took another square next to it, and then we took a square next to that, but that square had a side which was twice as long. Well, when I say twice as long, I mean the side of this square was such that I could put a whole square right next to those two. And then I can go and take another square and put it here. So that's another square. Okay? So now if I keep going, let's just keep making some more squares. I'll go over to here now, and I'll make another square. It's hard for me to make squares when my hand is blocking, but I think this looks sort of like a square. Now I'll connect it all up. Okay, that looks sort of like a square. And I'll make another square down to here. Yes, this is related to the golden ratio. Let's see what happens. So we just make another square down here, and I might have space for one more square. One more square over here. So this is not exactly what was asked, but I see that I can make an interesting problem out of this. Here's what we'll do. We'll now start to draw some quarter circles. And I'll draw some yes, this is the Fibonacci spiral that we're about to see. Quarter circles, which are like here, and then here, and then here. These are all quarter circles. So here we have all these quarter circles. The last one doesn't look so good. Once you have to draw things that are bigger, then it's more obvious that they're off. Okay, so I've drawn all of these quarter circles, and now let's go and find out what is the perimeter of this whole thing. Okay, let's do that. Let's figure out the perimeter of this, and we'll see an interesting pattern. So when you draw all of these together, these are all quarter circles, and what's the perimeter of each? Well, let's start with the inside. Let's pretend that the inside, let's pretend that the first square is 1 by 1. Is that okay? I don't know if you can see those pink ones, but it's 1 by 1. So what's the perimeter of that first quarter circle if it's in a 1 by 1 square? Does anyone know? What's the perimeter meaning what's the length of the quarters of a circle that's in that little square? Not quite 4, because I need to have a pi somewhere in it. This is a quarter circle which has radius 1, right? The radius of the quarter circle is 1, and so it's like 2 pi times the radius quartered. So it's 2 pi times 1 over 4. It's pi over 2. So this very first one is pi over 2 for its quarter circle length. That's pi over 2. TempID, nice choice with the emoji. That does work. So we have this pi over 2. Now over here, this is going to be also pi over 2. The second one's also pi over 2. And then after that, the next one, what is the length of this quarter circle here? This quarter circle has a radius of 2 now. And since it has a radius of 2, it's going to be 2 pi times the radius quartered. 2 pi times 2, and then divided by 4 is just pi. Okay? By the way, I'm already going to write down what this is equal to in an easier way. So this is actually also equal to pi over 2 times 1 plus 1 plus 2. Do you see what's happening? I don't want to keep writing those pi's. It's going to get annoying. Because over here, this one is going to be a quarter circle of radius 3. And if the radius is 3, then the diameter is 2 pi times 3. Quartered is divided by 4. So it's 3 pi over 2. That's what I would have for the next term. But that's just less nice to look at than to just say, well, it's 1 plus 1 plus 2 plus 3. Does that make sense? So now let's forget about the top row. The top row is just annoying. It's going to be plus something, and it will end somewhere. It will end somewhere. I don't mean it goes forever. I want this to end somewhere. I'm just going to write the thing on the bottom. It'll be 1 plus 1 plus, so it's 1 plus 1 plus 2 plus 3, and the next one is 5. Then the next one after the 5 is the 8, and then the 13. Plus 8 plus 13. And then it ends. Actually, now I can write down what it is on top. The last one on the top is plus 13 pi over 2. Great! So now I have all of this, and I happen to know that that happens to be this length of this spiral. But I wonder if there's a nice pattern. What is 1 plus 1 plus 2 plus 3 plus 5 plus 8 plus 13? Let's find out. 1 plus 1 plus 2, where can I do this? I guess I'll do it over here on the left. 1 plus 1 is 2. 2 plus 2 is 4. 4 plus 3 is 7. Actually, here's what I'm going to do. I'm going to start adding these up, right? I'm going to start adding these up. I'm going to say I had 1, 1, 2, 3, 5, 8, 13. And here's how I'm going to add them up. If I had just the 1, and I stopped there, let's make a table, sorry. This is the number. And this is the sum to here. Sum to here means adding from the beginning and stopping there. Okay, what happens? So the sum to here, if you just have the first one, is 1, because I have the 1 and I sum to here is 1. Now I take the 1 plus the 1 and I get 2. Then I take the 1 plus the 1 plus the 2, that's 4. Another way to see that is if the sum to here was 2, adding another 2 gives you 4. What is happening? So this is 4. 4 plus 3 is 7. 7 plus 5 is 12. 12 plus 8 is 20. And 20 plus 13 is 33. Does anyone think that this looks interesting? If you look at this sequence, something's going on. These numbers are kind of special. If you look at these numbers and you look at those numbers, they actually look like they're pretty close. After 13, it's supposed to be 21. We actually don't go to 21. That's not part of what I'm doing for this problem, but I'm just going to write it anyway. If I wrote a 21 here, the next one would be 33 plus 21, which is 54. After 21 would be 34. This would give me 88, and so on. And do you see what happened? I always got a Fibonacci number minus 1. So what I just found out is that if I add up all of these numbers, and I add up to the 13, what I get is 2 more Fibonacci numbers later, minus 1. So this, by the way, happens to be always true. And one way you can prove that it works is if you just look at this and you say, well, if I added it all the way to here, and my answer was the 34 minus 1, let me rewrite that there. Instead of 33, I'm going to write that this was 34 minus 1. Would it make sense that 34 minus 1 plus 21 will give you the next Fibonacci number minus 1? I guess that's our logo. But if you add this 34 minus 1 plus the 21, well, of course you get the next Fibonacci minus 1, because the 21 plus the 34 is the next Fibonacci number. And then there's just a minus 1. That's why this works. Actually, everywhere that I have this, since I just have this number and I want to add the next one, just because this number happens to already be the next one minus 1, then the answer should just be the next one minus 1. By the way, this is called mathematical induction. This way of proving something where you just say, well, if it was true up to here, then it's true one step later, is a method that you can use to prove infinitely many statements. In fact, what we've just showed is that when you go and add up these Fibonacci numbers starting from the beginning, you'll always get the next Fibonacci number minus 1. But I didn't take infinite amount of time to prove that to you. I just showed that if this was true in one stage, then it would be true in the next stage. Okay, so the answer to this question is actually quite nice. I just look at the next Fibonacci number, minus 1, and that just happens to be 33 pi over 2. I'm not sure if this was exactly the question you wanted me to talk about, but this is something that let me talk about Fibonacci numbers to show this neat pattern, and maybe to also talk a little bit about this idea called mathematical induction. What else can we do? I see that somebody has made a lot of requests to explain permutations in a practice problem. One thing I'm trying not to do here is I'm trying not to give things that are actually part of normal classes. One reason is because you already have classes. Those are things that might be taught in the classes. Another reason is actually those I already have lessons on. Those happen to be part of the online school that we run, the Daily Challenge with Po-Shen Loh. So I prefer not to just rehash the lessons that are already there. Rather, I like to use this opportunity to kind of connect lots of different ideas that we might see in math and outside. What else do we have here? So Ranbo Song asks, how many prime numbers are from 0 to your age? That requires me to know how old I am. I don't usually think about this that often. So let's see. What year is it again? I also lost track of that because the world's been crazy. It's 2020. Okay, then I think I know how old I am. Right? Now, if I want to tell you how many prime numbers there are, my instinct is it's probably... I think it's 12. I think there are 12. I think there are 12 prime numbers between 0 and my age. Now, let me tell you something about prime numbers. So the way I was able to think of that relatively quickly is that, oh, yes. How'd you guys know that? I told you it's 37. Okay. I guess at this point, if you look on Wikipedia, you can probably figure that out too. What? Somebody already did that. Okay. By the way, I have no idea who's writing my Wikipedia article. Occasionally, I just see random new things appearing there. Hopefully, they're correct. But now let me talk a little bit about prime numbers. It's just because when I think about primes, the way I can answer that question for you quickly is by the way that the primes happen to be laid out. So somehow in my head, when I think about prime numbers, I see this kind of a pattern. The one-digit primes, the primes that are less than 10, are 2, 3, 5, and 7, not 9. And then the primes that are between 10 and 20 are 11, 13, 17, and 19. Then the primes that are in the 20s are 23 and 29. And then there are two primes in the 30s, 31 and 37. And then in the 40s, you get three of them again, 41, 43, and 47. Somehow, these are some of the most common prime numbers that you run across. And just this picture is stuck in my head of there are 4 primes in the single digits. There are 4 primes in the teens, like 10 to 20. And then there are 2 primes in the 20s and 2 primes in the 30s. And having this kind of a knowledge in your head is useful if you're ever trying to calculate something fast, like how many primes are there up until a certain number. So when you asked me this, I was like, well, okay, am I actually 37? I had to think about that. But if I was 37, it was like, okay, great. I got the 2 primes in the 30s row. So it would be 4 plus 4 plus 2 plus 2, which is 8. So I'm just sharing that because if you see these primes a lot, after a while, if that kind of a picture can stick into your brain, then you'll be faster whenever you figure any of these questions out. Let's see. What else do we have here? Ooh. Judy Andy asks, how can you figure out how many prime numbers there are between 2 and 2,500 in a fast way? This is a beautiful question. All right. Here's the dumb way to do it. You go through the numbers 2 through 2,500, and what you do is you go and say, is 2 prime? Yes. Is 3 prime? Yes. Actually, this doesn't seem dumb at all. This is pretty easy. Is 4 prime? Well, let's check. Divide 4 by 2. Nope, it's not prime. You know, let me try to write some stuff. Here's a way that seems reasonable at first. Is 2 prime? Yes. Is 3 prime? Yes. Is 4 prime? Divide by 2? No. Okay, no more 4. Is 5 prime? Yes. When I say yes, I try dividing 5 by 2, try dividing 5 by 3, and so on. I don't have to divide 5 by 3, by the way. You only have to divide up to the square root, because if something is factorizable, then one of the factors is less than or equal to your square root. How about 6? Well, 6 I tried dividing. Okay, dividing by 2 doesn't work. I guess I should write a yes. I don't know how I decided to do this. Okay, great. 7, you just keep going. And after a while, you go for a while, and then you realize that this is not so great. After a while, you say, oh, here's a number I need to figure out. How about 1,728? Okay, that's too obvious. That's obviously not prime. It's even. 1,729. That, by the way, is a beautiful number. This is called Ramanujan's number. This is the smallest number that can be written as the sum of 2 cubes in 2 different ways. Okay, great. But is that prime? Is 1729 prime? Does anyone know? Well, all I can do is I can start dividing by stuff. I can divide by 2, doesn't work. Can I divide by 3? That doesn't work. There's a trick for figuring out if it's divisible by 3. Divisible by 5? It takes forever. And I actually don't know. Is 729 prime? I don't even know. Maybe somebody knows. What is the prime factorization of 1729? What you see here is it's painful. We're basically saying every single one of these numbers I need to go and try, and I need to go and try to figure out dividing by stuff. Oh, you're saying it's divisible by 7? Let's try. Somebody said it's divisible by 7. I'm curious. I want to learn because this is a very important number. Well, important because it's famous. 7 times 2 is 14. Okay, 32. 7 times 4 is 28. Oh my gosh, it is! Wow, 247 times 7. Who would have thought? Okay, this is why this method is awful. Oh wow, you can even keep breaking it apart? So 247 people are telling me that they can even break into smaller pieces. That's neat. 247, they're dividing by 13. Oh, here's what I'm going to do. I don't want to divide by 13, but I know how to multiply 13 times 19. Some people are claiming that 13 times 19 works. Do you remember how I do this? Do you remember how I multiply teens? We talked about this in another one of these daily live streams. What I do is I just add the 9 to the 3. That's 22. And I leave a blank. And then I do the 3 times 9, and that's 27. So, okay, that's supposed to be 27. But since it's 27, I add 2, the 20 part, the 2. I add the 2 to that 2, and that gives me 4. So actually, you can do this in your head. 13 times 19, add the 9 to the 3, so I got 22. It'll be 22 something. Add this 27, 247. So it works. Okay, so we just found out that this is very much not prime. It can be split into 3 things multiplied together. Now, when you look at this, this is terrible. Do you really want to do this all the way to 2,500? No. So there's something else. There's something called the sieve of Eratosthenes. And the sieve of Eratosthenes works like this. First, the hard part is you have to write down all the numbers from 2 to 2,500. That takes a while. Actually, if you really wanted to do this, you wouldn't write all of the numbers. You would do this. Does anyone know the fastest way to write all the numbers from 1 to 2,500? Oh wait, this is not 250. This will maybe take a while. So I was hoping to do something which was, well, you know what? I could still do this. Yeah, 2,500 works. Here's how I would do it. If somebody actually asked me to try to do this, here's how I would do all the numbers from 1 to 2,500. I would draw a big square. On top of the square, I would write in some very small words, 1, 2, 3, up until 50. And then down here, what I would write, oh, this is interesting. Actually, at this point, I want to be a computer scientist, okay? Computer scientists don't go with 1 at the beginning. They go with 0, and that's more convenient. I'll go 0, 1, up until 49. And I don't need to worry about 2,500 itself, because that's obviously not prime. 0, 1, up until 49. And then this is supposed to be a giant graph paper. So what I do is, I have all these lines. And I don't write any numbers inside them at all. This is a giant graph paper. Not sure if this makes sense. You can just go and get a giant graph paper and you do this. And it has lots of squares inside it. By the way, if you just found a giant graph paper and you just got 49 squares, 50 by 50 chunk of the graph paper, this would work. Now, why do you do this? The reason you do this is because every single one of these squares corresponds to a number between 0 and 2499. What's the number it corresponds to? It's like this. If I have, for example, row number, let's call it 7. If I have row number 7, I mean the row with 7 in front, which is, by the way, the 8th row because I start with 0. If I have this row with a 7 on it, and if I have another row somewhere else which has, I don't know, maybe this is like 23. The row with 23, actually I can't be 23 because that's beyond half, and half of 50 is 25. So let's pretend this was 33. That's still not drawn to scale. I don't know, call it 29 or something. Looks like a 29. So if that's 29, this square here represents a certain number. This is not a multiplication table. What this represents is the top row represents the numbers 0, 1, 2, 3, up until 49. That's what those represent. This square here represents 0. This square here represents 49. This square here represents 50. And this square here represents 99. Does my picture make sense? I'm just imagining that each of those squares has a name, 0, 1, 2, 3, up to 49, because there are 50 squares across. So 0, starting from 0, 0, 1, 2, up to 49, 50, 51, 52, 53, up to 99. And I just keep going across and across and across and across, and you go, and the very, very last number you get, by the way, this very last square, this will be 2499. The reason that it's 2499 is because there are 2,500 squares in this table, and that was 0 up there, so 0 to 2499 is 2,500 numbers. By the way, if I see a 7 here, and I see that it's in column labeled 29, can anyone tell me what number that corresponds to? Does anyone know? Oh, I left out 2,500, Philip Neller, you're right. However, the reason I left it out is because I said we don't need to worry about 2,500. 2,500 happens to automatically be not prime because I can see a way to factorize it. So I don't actually care about the 2,500. And it's a little bit easier to think about these tables or array. I want to call this an array because that's what you call it in computer programming. It's easier to think about arrays in terms of starting with 0. And I see some people have some answers already. What number should go here? It's not a multiplication table, right? It's going all the way across 0 to 49 and then 50 up until 99, and it just keeps going across and across and across. So what number would be in this position? The way to think of this is, let's start with this. What number should be at the beginning of this particular row? Right? At the beginning of the first row is 0. At the beginning of the row with a 1 is 50. At the beginning of a row labeled with 2 is 100. This is actually very nice. The beginning of the row labeled with 7 is just 7 times 50. Did that make sense to people? It's because I start with 0, I get 50 across and 50 things across. Later, that means that after doing 50 things across, this should be at 50. And then you go another row of 50, and the next one should be plus another 50. So this number right here is exactly 7 times 50. The number that's at this square is 350. If that's true, if that square is 350, and that happens to be in the column 0, what goes here? So this is like a algebra type problem, or the kind of problem you see in some kind of math contest of, oh, I see. So if that's the thing in the column labeled 0, then in the column labeled 29, what should I do? What should I do to 7 times 50 if I want to know what goes there? It should be 7 times 50 plus how much? Well, I should plus 29. Because at this one, which is the column corresponding to 0, that's 7 times 50 plus 0. And the next one is 7 times 50 plus 1. And I should go all the way to 7 times 50 plus 29. And now I see that there are some answers. That is equal to 350 plus 29, 379. Okay, so that's 379. That goes right there. And this just shows that we are able to think of every single one of these squares as a particular number between 0 and 2499, including 0 and including 2499. In fact, the rule is very simple. The rule is you just take the row number times the 50, it's 50 across, the row number times 50 plus the column number. It's beautiful. It's just such a simple rule. And that's one reason why I like to start these things at 0. If I start them all at 0, I don't need to write all kinds of weird times something minus 1 or whatever. And by the way, this will also help answer, somebody asked a question about coding and math. This thing I've just done, this is exactly how you do stuff in computers. In a lot of computer programming languages, you make a two-dimensional array exactly like this. And inside the computer, that's how they go and figure out, this particular square in the two-dimensional array, which position is it after the beginning. Somebody said you're confused. Let me see. So if you're confused, oh yes, why is it 7 times 50, but it's plus 29? Or I should be pointing here. All right. So first of all, why is this one 7 times 50? This square is 7 times 50 because the first square is 0 times 50, and the square right under it is 1 times 50, and it's 1 times 50 because it's like 50 later, right? If that's 0, the last one is 49, and then 50. So this first column is always just whatever is the row number times the 50. 50 is how many I'm going across. These numbers that are on the outside of the table, you don't care about. Not that you don't care about. Those aren't squares, right? So when I look at this particular square is called 7 times 50. And then if I want to know what is this square, you can see a pattern even. Here, when you're in the row corresponding to 7, and in the column corresponding to 0, your number of that square is 7 times 50. Why not 29 times 50 and 7 times 50? Tissue Boy has a question. So why not 29 times 50? I think I should have said, how are these being labeled? I'm imagining that, this is actually a table where every single one of the squares has a label, and I labeled the squares 0, 1, 2, 3 up to 49, 50, 51, 52, 53 up to 99, 100, 101, 102 up to 149. That's how we're going across, right? We're just going and labeling all of these, okay? And then so if this particular one is labeled 7 times 50 plus 0, the one right after it is labeled 7 times 50 plus 1, 7 times 50 plus 2, and so on, all the way up to 7 times 50 plus 29. How much I plus is just depending on what is the column label, all right? So, okay, so we have this thing now, and what I have is now when I draw this picture actually already represents the numbers. And I don't need to, in fact, even write the stuff inside. So I don't need to write the stuff inside. The inside already corresponds to numbers. Now here is how I figure out what's prime. The first thing I do is I want to strike out all of the multiples of 2. 2 is the smallest prime number. But let me start with something else. 0 is not a prime number, okay? And 1 is actually not a prime number either. We get rid of that too. The reason that 1 is not a prime number is because if you wanted to prime factorize and you wanted to say factor into a product of the primes, 1 is not useful because you can always stick a 1 in there. Primes you should think of as like the ingredients of a number. And so 1 is not useful as an ingredient of a number. Now let's start. What we do is we go across. And what we happen to see that the 2 has not been struck out yet. This particular square corresponds to 2. Since this square hasn't been struck out yet, 2 is prime. So 2 is one of our primes. And I say, great, I found a prime. Yay. And then what I do is I say, great, the 2 is a prime. Now let's get rid of all the multiples of 2. So what happens is that there's going to be something which has a 4. The 4 is probably here. We knock out the 4. We also knock out the 6. And we just knock out all of the multiples of 2. So you kind of go across. This is not drawn to scale, obviously. But you go and knock off all the multiples of 2. And they are here. This is multiple of 2. It actually is quite a nice pattern. But you just kind of go across this whole thing, knocking away all the multiples of 2. When you're done with that, you go and look at what's left and you say, what's next? Oh, 3. I didn't knock it out yet. If I didn't knock it out yet, it's prime. Hooray! That's 3. And now that I've chosen 3 to be prime, I will go and knock out all of the multiples of 3 after that. So after that, I get 3 times 2 is 6. Oh, I already knocked it out, but that's okay. Doesn't matter. It's knocked out. I knock out 9. And you just go on and you just X out the things that are multiples of what you just picked. And then you look. Okay, 4 has already been knocked out, so it's not prime. But the next one here is still open. So that means it's a prime. You see, the rule here is that I'm just going to go and move across my chart, and every time if I get to a square and it hasn't been knocked out yet, well, then it's not divisible by anything I had before. So in that case, I can just go and say that's a prime, and then I go and use that number, and I knock out all the multiples of it as I keep going. This is actually pretty fast. If you use this procedure, what you'll do is you'll look at each of these numbers at most once, and when you look at that number, you'll at most hit all the multiples as you go down. And it actually gets faster and faster. If at some point you go and find out that, oh wow, here's a prime, if you can imagine what happens when you take all the multiples of it, it's actually off the chart. So the number of things you strike out is the most at the beginning. And later on, when you go and find some prime that happens to already be in the 100s, if the prime number is in the 100s, you strike out all multiples of it, and the number of multiples of a number in the 100s that are less than 2,500 is at most 25. So that's what you do. And this is called the sieve of Eratosthenes. You just kind of go through from the beginning, and you go and strike out all of these things that are multiples of whatever are the new primes that you found. And what's left will just be the primes. Okay. Other questions? What else do we have here? So I'm looking, Oh no, somebody said, wait, I can't come tomorrow. No. Well, the good news is that I believe that these daily live streams are recorded in the sense that you can at least see them for one day. We don't keep all of them around because that would just be too many. But if you can't be here tomorrow, just you can still follow with the live stream. Although I do think that the most fun part is not the math part. Well, okay, I think the math part is fun too. But I think that one of the most fun parts is the interaction with everybody. So it's best if everyone can come together. What else can we do? Oh, this is neat. Here's a question that's not about math, right? It's do you believe, Christopher Liu asks, do you believe the UFOs sighted by Air Force fighters are real? There were indeed some videos released by the Pentagon about some UFOs. Here's my opinion about aliens and UFOs. If we ever meet aliens, most likely, either they are super advanced compared to us, or they are super behind compared to us. Why do I say that? The reason I say that is because if you know how long it took for life on Earth to become the way we are now, as we know it, it took like 5 billion years or something. The sun is 5 billion years old. So 5 billion years, that's a lot, by the way. 5 billion is like this. That's 5 billion years, right? How long has our human civilization even had the capacity? So that's years. So that's 5 billion years. Do you know how long our human civilization has had the capacity to fly Air Force aircraft that can go and look for UFOs? You know, it's like, it's not. I mean, if the UFOs came when we weren't even like humans, no one would have noticed. But even if they had come at a time when we didn't have a Air Force plane that can go and see them, you know, we wouldn't have noticed either. So like that's how long the Earth has been, and how long have we been able to? How long have we been able to actually go and get up close to something like this? You know, like 50 years maybe. So, you know, this is like 5 billion years, and after those 5 billion years, that we're finally in this like 50-year gap that we can go and see this stuff, right? Great. What's the chance that some alien civilization evolved at exactly the same speed as us, or almost the same speed as us, so that while they were going for their 5 billion years, it just so happened that they got to this point now? You know, like if we got to this point now, we got to fly like 50 years ago, who knows? If you gave us like 300 more years, we might be able to do a whole lot more. But even if you put 300, you know, like what could we do in 300 years? Look, if we all work together and try to save humanity, hopefully we'll have another 300 years to live. I don't mean individually, I mean as a civilization. But you know, like, that's still nothing. So the point is, when you go and look at all of these, the potential for alien life, most likely, if they were to suddenly meet us, like their civilization would either be ahead of us by like 1,000,000 years, or our civilization would be ahead of them by like 1,000,000 years. 1,000,000 years ago, we weren't doing anything interesting. Now, there's something that if they were the ones to meet us, then probably they're the 1,000,000 years ahead of us. Then what I'd say is, oh no, I hope that they're peaceful, because if they happen to have all of that capability to fly all the way from their solar system to our solar system, they're probably pretty capable. And if they're like 1,000,000 years ahead of us or 1,000,000,000 years ahead of us, we're in big trouble if they decide to squash us like, you know, like ants or something. So my opinion is, I sure hope those are not real UFOs, because if they are, we are in deep trouble. By the way, they're quite possibly just like other things that are flying around. So you never quite know. Okay. Christmas Warrior 3847 says, no one is peaceful. We are all greedy. You know, that is true. And that's the problem of human nature. In some sense, that's why we have instability in our human civilization, because we unfortunately are all greedy. And so the hope is that somehow we can all figure out a way to get along before that greed ruins everybody. Let's do some more question. One last question. What can we do to finish this? Whoa, that's cute. Let's finish this one. Chen Lai asks, if one stays in the sky, after 12 hours, can he get to the other side of the world? So that's pretty interesting. You know, like if you just stay in the sky, what you're saying is you stay in the sky and you let the Earth, wait, the Earth doesn't turn this way. The Earth kind of turns this way, right? Right, so if you stay in the sky and the Earth turns, that would be great, right? That's a pretty clever idea. The only problem is it's actually quite hard to stay in the sky, because you first have to move opposite the direction of the Earth and get your speed so that your speed happens to be going in the opposite direction of the Earth at the normal speed that you need to stay in the sky. And as we saw in an earlier live stream, if you were on the equator, that means you were getting 1,000 miles an hour. Now, that's not easy. It's especially not easy if you happen to be in the atmosphere, because then you're not just staying in the sky. The wind is blowing against you like crazy. So the answer to your question is, if you were able to just kind of stick there while the Earth turns, yes, that would work. But that's quite difficult to do from a physics perspective. Actually, in a physics perspective, if you wanted to just stay there, you wouldn't. You would get sucked into the Earth by gravity. What you need to do is you need to have some very, very powerful rockets that could accelerate you constantly to sit there in the sky, and you need to be high enough so that you're not going to have the wind blowing against you. But that's a pretty interesting idea. Yeah, that's a pretty interesting idea. New way to travel. The new way to travel is just to somehow find a way to stay in the sky. Well, with that, I think we unfortunately are at the end of our time for today. I hope that you had some fun today. And again, I'm watching these numbers that are following that are coming to this live stream every day. I have noticed that it's been going up, which is neat, but it also somehow is going up and stopping. If you happen to like what you see, please do tell other people. I have a goal of trying to help as many people as I can. And judging from how much fun everyone seems to be having over there, it seems like something that more people might like to join too. I'll be back tomorrow, same time, 4:00 p.m. Eastern Time. We'll have another discussion for another hour, and who knows what we'll talk about. Until then, I wish everybody a very, very good day, and good luck. Stay safe.